that into just basic citrus irrigation scheduling on with this presentation, looking at maximizing nutrient uptake and minimizing leaching. So the key questions you need to ask when you're considering irrigation scheduling options is, how deep do I need to irrigate? Whether you're on the ridge or on the flatwood, we all know that the root zones are different, and we'll talk a little bit about that as we go. Now with greening, they're even different yet. How deep do my roots grow? And that's the answer to how deep do I irrigate. How much water does the soil contain now? When I'm considering irrigating, that has to be determined and should be known before you irrigate. We want to look into how dry the soil needs to be before we irrigate, and then how long do we irrigate after we determine that we need to apply an irrigation. This is results of a study that we did on ridge soils in this case, but they apply pretty well to flatwood soils. We looked at tree density and found that, as we all suspect, that tree density decreases with distance from the tree, also decreases with depth from the soil surface. And it was very consistent over the trees we did, the mature trees, and it was even consistent to rootstocks. The rooting pattern changed based on the two different rootstocks we used, Carrizo and Swingle. We usually think of those two rootstocks as being very similar to each other. In this study, we found some differences in that Swingle roots were very close to the surface. Carrizo went a little bit deeper, and that influences our decisions for irrigation scheduling. So we need to concentrate, whether you're on the ridge or the flatwood, you need to concentrate on that 12 to 18 inch depth. That's where the majority of your roots are. If you're on the flatwoods, it's more like 12. If you're on a ridge, it's about 18. But you can irrigate a little deeper and possibly take those roots down to a 24-inch depth. So looking at the effect of soil on root density, specifically spodosols that we have mostly in this area, the citrus trees, as I mentioned, form this thick mat of roots, and we'll see some photographs in a moment that illustrate that very nicely. And generally, 1/3 of the root system will be on the furrow side of the bed, 2/3 on the crown side, because that's the higher, drier part of your bed. So when you look at modifying your beds, you need to, or where you're putting your irrigation, you need to irrigate closer to the bed side rather than the furrow side. The A horizon, which is typically the top horizon, the one that contains the majority of the organic matter, that's the one you need to look at. That's where the roots will be, even if you've taken soil from the swells and put on top of the A horizon that was there previously. The roots will be in that A horizon, not in the soil that you've put on top of the beds. These are some photographs that I took after some of our tropical storms came through in 2004 to 6. This tree was damaged where we had some water issues. The soil didn't drain for a period of time. You can see how thin the root system is. Very few feeder roots here, but you still have that mat of roots right at the surface. This is the canopy, so this would be right at the surface of the soil. This is a healthy tree that we pulled up, and you can see the same thing. The mat of roots at the surface, the thin, fine feeder roots here, much more dense than you have in this damaged tree. And this is exactly what you'll see with greening when that occurs. We've looked at that. Jim Graham and I have done some studies on it, looking at root loss from the time they're infected. The first thing that happens with a greening tree, once it gets infected, is it loses roots, somewhere between 30 and 50% of its feeder roots. And so you'll go from a good, healthy root system like this to something like this. That's very sparse and has a thin root system. So that needs to be kept in mind when you're considering your irrigation. And we'll talk about how to do that. Looking at our soils, this is a loam soil. Field capacity of loam soils are typically around 35 to 38% in that neighborhood. 25 to 50% are the typical targets for irrigation scheduling as far as depletion of allowable or available water. So if you deplete 25% of your available water from about 38%, that means you're going to irrigate at about 28, 29%. If you let it drop down to 50%, which you can do certain growth phases of certain crops, you're in about 20% soil moisture with a loam soil. In our sandy soils, our field capacity is much lower, typically 8 to 10%. That's about all our soil will hold against gravity. The rest of the water drains out of the soil. Then as roots in the soil uses up the moisture, our 25% depletion is now about 5%. Our 50% depletion is about 4%. So we have a very narrow range that we're dealing with, and we've all seen that. We all deal with that as far as irrigation scheduling, but those are the things that you have to keep in mind when you're considering your irrigation activities. This is the same slide, just a little more detail, going from a 7.5 to about a 5.5% water content for 25% depletion. But what we have recommended in the past for citrus irrigation is in the spring of the year, from late January to early June, having no more than about a 25 to 33% of allowable or available water depleted from your soil. This will keep the soil a little wetter, keep the trees flushing, flowering, and support the fruit set. As we get into later months, going through the rainy season starting in June and ending up in the fall, we can go somewhere between 50 and 66% depletion without damaging your crops. Now, these numbers are from research that was done prior to greening. Greening is changing everything. We have some studies going out right now in both in groves and in greenhouses, and I'll talk about those at the end of the talk. But we're looking at how this now changes. We're probably looking at keeping the depletion somewhere around 25 to 33% year-round, as opposed to letting it drop because of these fruit drops that we've been having late in the season prior to harvest. We thought initially was primarily due to water stress, but these studies will tell us whether that's true or not. Some growers were over-irrigating, trying to overcompensate for what they thought was a stress, causing fruit drop over the last couple of years. We didn't see that helping at all. You just have to keep that depletion in the root zone up in this upper or lower depletion area. So looking at soil moisture sensors, that's what we're recommending as the best way of irrigating any crop, but particularly citrus. This is what you would be looking at. You would look at your field capacity. You can see after they've irrigated here, the water content goes up. It comes down, and where it starts tapering off with only root activity extracting water, that's where your field capacity is. So at the upper depth, that number is somewhere around 8%, somewhere between 8 and 9%. So that's your top number. Your 25% depletion, you can calculate that out. Available water is field capacity minus the permanent wilting. In our soils, permanent wilting is roughly about 2%. So if this were 8% field capacity, available water would be 8 minus 2, so it'd be about 6%. 25% depletion would be about 1.5%. So you're at 6.5% at your 25% depletion level. So you want to watch your soil moisture. When it gets close in your primary root zone, in this case would be between 10 and 40 centimeters, as that approaches your 25% depletion, that's when you want to irrigate your crop. You don't want that to go below your 25%. But you also want to keep a water probe down here at a deeper depth below your root zone, and you don't want that to move much at all, which they're doing here. Okay, to calculate water content, we need to know how much water the trees are using. For any crop, we call that evapotranspiration. Evapotranspiration is just the combination of loss from the soil, from the plant as it transpires water out of the plant, and from transpiration from leaf surfaces and soil. So you add those two together, you get evapotranspiration. Those can be determined from weather observations, from weather data, using a model that's been calculated for a grass crop. That's the kind of the standard, is to use a grass crop to determine what we call reference evapotranspiration. And that's what ETO is, reference evapotranspiration. So that would be calculated for a grass crop. So you would take that number, your reference ET, multiply it by a factor that is based on your crop and a growth phase for your crop. We have that for all the crops grown in Florida and citrus as well. So if you multiply these two numbers together, you get your crop ET, ETC, and that's how much water your trees are using. This is just a basic example. This happens to be a corn crop. The blue line is how much water the corn is actually using. So as the corn gets larger, gets taller, it's using more and more water, comes to a maximum. Then as the corn matures and dries, it uses less water. The red line is your reference ET. So as you go through these months, it starts out fairly low, goes to a maximum in the middle of the summer, and then starts going down again. So this difference is your KC factor. So you would calculate the KC for these two areas in order to determine how much water is being used based on your reference ET. In Florida, this is a diagram of what evapotranspiration looks like, starting in January of each year, going to December. You start out at 0.07 inches of water per day. That's the reference ET, using a Penman equation, just from weather data. It increases through the year, comes to a maximum in early June of about 0.2 inches of water per day, and then falls back down to that 0.07 inches per day. This is the kind of information you can get from fawn, and we'll talk about that in a moment. Looking at KC values, we've calculated that for mature trees. KCs start out in January at about 0.8, upper 0.7s to 0.8. So this is telling us that it's using about 80% of reference ET. So about 80% of what a grass crop would use, that's how much your trees are using. You get into the middle of the year in June, and you're over 1. So this is 100% of your reference ET, 1. We calculate the maximum at about 1.05. So it's using just a little bit more than a grass crop would. And then as we get into later in the season, that KC goes down. Now for young trees, 2 to 5 year old trees, we've calculated it starting much lower, just because they're smaller trees. But during the high part of water use, they're using as much water as the mature tree, because of the open ground underneath the tree is evaporating and losing water. So these are the types of numbers that you would have to have if you have a reference ET, you have a crop coefficient for citrus. I'll explain the KS in a moment. You can determine your ETC coefficient. This is the soil drying, the KC values. For most crops and most soils, heavier soils, this value would be 1, which means you don't need that number in the equation. If you're multiplying ET times KC times 1, you don't need it there. It's giving you the same number. Typically for most soils, this bar comes out to about 25 or 30% depletion of soil water. So if you're within 25 or 30% of soil depletion, you don't need to be worried about this KC factor. But what we found out in our sandy soils is that shortly after you irrigate, if only 5% of the soil moisture has been depleted below field capacity, you're starting to use less water. The trees are using less water than you would calculate just using ETO times KC. So we've included this soil factor. So that's the equation that we end up with, that we have to have in order to determine the amount of water to use for most of our ET-based models. And a talk that I have later in this presentation will get us to that, and we'll look at those models. Irrigation requirements, I've talked about a bit of this, but in the spring, our recommendation to support the flowering and flush fruit set, we have the tree has different requirements during the summer, which then all you're worrying about is additional flush and fruit enlargement. The 25 to 33% depletion during that spring period is our current recommendation, 50 to 66% during the remainder of the year. This will likely change, but we don't have the data for it now. So looking at water use and water time, these are the kinds of data that we need, or information we need from our soil. We need the field capacity, how much water the soil can hold. We need to know what our minimum allowable depletion is, whether it's 25% or 50%. We can convert that into a number if we know the field capacity. We need the root zone depth, the area that's wetted by the microsprinkler, and the microsprinkler flow rate, tree spacing. We'll go through these equations, but with our models that we'll show you later, you don't have to calculate these, but if you want to, just to understand the process a little better, we have, as an example, we have a field capacity at 6%, which is 0.6 inches per foot. We have a maximum depletion of 50% in this case, root zone depth of 3 feet, sprinkler coverage of 60% of the soil area. The flow rate is a blue jet at 16 gallons per hour. Tree spacing is 22 feet by 12 feet. That would give us 165 trees per acre. So we take the 0.6 inches per foot, multiply it by the 3-foot depth, and we have 1.6 inches of water that the soil can hold. 50% of that would be 0.9. So when we've used up the difference between these two, which is 0.9 inches, that's when we need to irrigate in this example. Looking at feet of water required, if you have 0.9 inches of soil, you divide that by 12 inches per foot, you get 0.075 feet of water would be required to fill the soil back up to fill capacity. Take that 0.075 feet, multiply it by the area of the tree. That's 19.8 cubic feet of water. 19.8 cubic feet times 7.48 gallons per cubic foot. And that gives you 88.6 gallons of water per tree. Take that 88.9 gallons for water per tree, multiply by 165 trees per acre, and it would require you to put out almost 15,000 gallons of water per acre for this example. The run time for that, if you have the number of gallons per tree, you divide that by your 16 gallons per hour, you come up with 5.6 hours runtime. Our systems are 100% efficient, our irrigation systems. This would be the runtime if it were 100% efficient. Micro sprinkler is about 90%, so you divide that by 0.9 and you come up with 6.2 hours that you need to run that system. The models that I'll show you in a moment do this calculation for you, so you won't have to do that yourself. I'll go through this fairly quickly, but this is just looking at how this depletion affects the amount of water you apply. So if you have 25% depletion on a June day, the ET is 0.21. Whether you're going to deplete 25% or 50%, it's still 0.21 inches per day. You look at your field capacity, and that's 1.65 inches of field capacity in your rooting zone. 25% of that 1.65 is 0.41 inches. 50% of 1.65 is 0.83. And so this is how you would determine the days between irrigation. At 25% depletion, you're looking at 2 days between irrigations. 50%, you're up at 4. This is just some slides I have on types of scheduling methods. We've talked about guidelines using tables. We have that available in our EDIS documents and on the FON site. We can look at soil moisture status, which is the soil moisture sensors. Those can be expensive to maintain and to operate, and can require high labor input. The water balance model requires less labor by the users, but requires information about the field and the irrigation system and is computer-based. So this is a typical type of schedule you get. This is the EDIS document, HS 958, where you can find these types of schedules. But you have the month of the year, you have the historic ET for that month of the year, and then this gives you an idea of intervals between irrigation events that you would maintain. And you can see that during the winter you have quite a spread, and then it goes down into the high demand months, not between 2 and 3 days, and quite often 1 day between irrigations. The duration decreases as you get those intervals closer together. This is an example looking at root zone depth. If you go through the calculations that I did before, looking at 12, 18, and 24-inch depth, these are the types of schedules that you would look at, or you would see. In May, you'd be 1 to 2 days between irrigations for 1 or 2 hours if you only have a 12-inch depth. If it's 18, it's 2 to 3 days for 2 to 3 hours, and a 24-inch depth is the same 2 to 3 days, but you can increase the runtime to 3 to 4 hours to get water down to that 2-foot depth. I'll go through this very quickly. You know most of this already. Manual operations is just looking at feeling the soil, the old kick the dirt method, looking at tensiometers. You have some handheld sensors that I'll describe, some portable electronic sensors, and then you can automate these electronic sensors into your current irrigation scheduling if you have control systems that will allow. When you're looking at the root zones, you need to consider that the sensors need to be placed within the soil where the majority of the roots will be found. That's very important, and the depth that they will be found. You need to have multiple sensors used for the crop for different depths within the crop. You need to look at the root structure if it's going to change. If you're looking at small trees, initially dealing with small trees, you need to move those sensors out as those trees increase in size to keep in that maximum root zone. And soil structures can also limit the root zone, such as a spodic layer and a chronic high water content. That's something you need to look at when you're scheduling irrigation. So you have two different types of sensors that you can buy and use. The electronic sensors looks at content, water content. Tensiometer looks at water tension. Two different numbers that come because of those curves I showed you looking at water reductions can give you a lot of information on when to fill your irrigation. These are some of the content sensors. You have some sensors that have different depths built into them that go inside of an access tube in the ground. This is a smaller unit. This is a larger unit that goes into an access tube in the ground, goes to a data logger, and that can then be radioed back to a central location. You have sensors that are buried in the ground directly, so you would have one sensor at each depth that you want. This is a capacitance sensor, and then you have TDRs. In our soils, TDRs work very well. Initially, we had some problems with TDRs, 10 or 15 years ago, but now they are working very well. This is your tensiometers. I'm sure most of you had seen them. Just a tube, empty tube that you fill with water, has a ceramic tip that water goes out into the soil to re-wet the soil and creates a vacuum within the tube, and the vacuum is read here. So you're not getting direct water content, you're getting the vacuum that the water is held at within the soil. And that's a good indication, but these require a lot of maintenance. Some of the electronic sensors do similar things, give you the same type of number, but don't require the maintenance of a tensiometer. So to conclude this talk, we looked at root distribution. That has to be key in your decision making on where to put your sensors, how deep you're going to irrigate, how large of a wetted pattern you need to irrigate. You need to look at the water quantity and quality issues that will impact your situation. The next speaker will be talking about salt issues. They have to be handled in a different way as far as irrigation scheduling. And then we ended up looking at 3 methods of irrigation scheduling, which are guideline tables, sensors, or models. And we'll have more on the models later this morning.